Hello everyone, welcome for this lecture. Today we are going to solve numerical on faults, unsymmetrical faults. We'll see one numerical and similarly kind of numericals we can easily solve. Okay, so we'll see how it will be. Okay, so this is the numerical of on LL faults. Okay, so now we'll see. Okay, we'll see how it will be. The power system shown. Okay, the power system shown below. Okay, this is the power system what they have given. On this it is on no load. Okay, the per unit reactance of all the apparatus they have mentioned means we need not calculate new values of reactances in per unit. Okay, they have already mentioned. See, observe, this is first generator and machine 1, machine means motor 1, motor 2. Okay, all these, and we have a transformer. Please be careful, this is a transformer 1, this is transformer 2, and this is transformer 3. Okay, don't take it for it is T1, T2 and all. It is a T1 and it is T2 and it is T3. Okay, so that is the only thing we supposed to remember, and these are the lines L1, L2 and L3. So based on this they have given each values. Okay, so generator they have given it's a positive, x1 represents a positive sequence impedance or a reactance, negative and zero sequence reactance. Okay, transformer they have given T3 means a transformer third, also they have given line L1, L2 and line L3. Okay, each element means each component of a power system has these all reactances, positive, negative and zero sequence. Okay, even our M1 and M2, motor 1 and motor 2 has positive is 0.3, x2 is 0.1 and 0 is 0.1. Okay, so all these things, which fault has occurred? A double line fault has occurred. This is nothing but LL line to line fault takes place at the HD side of the transformer 3. Okay, right here this fault is occur at HD side of the transformer. Okay, determine the current at the fault point. You need to calculate the fault at this point. Observe, all this generator is connected here to the transformer T3, and from this there is line 1, line 2, and again after line 1 we have a transformer 1, M1, and then from this we have L3, right? So based on this we supposed to draw the circuit diagram. Since already they have given all the values, we need not calculate any new values. Okay, based on this we'll draw the circuit diagram. Okay, see, so how it is, first generator. Okay, so it has the impedance of xg, right? It has already mentioned, it is generator and a transformer T3. Okay, and then we have a line 1, and then here we have a line 2, and here we have a line 3, and from this transformer 1, and you can take it as a motor 1 along with that source, and here after a line we have a transformer 2 and a motor 2. Okay, like this we have to draw. And remember one thing, this is a line to line fault. Therefore to calculate a fault current, so what's the formula? You can recall once, it is EA divided by, means IA1 or IF will be equal to IA1 or IA1 will be equal to. Okay, then once we calculate IA1 we have to calculate IF. IF is nothing but root 3 times of your root 3 times of your IA1. So alright, so that we have to take root 3 times of IA1. Let's calculate first IA1, which is equal to EA divided by Z1 plus Z2 plus ZF. Okay, Z1 plus Z2 plus ZF. You can observe in this formula. Okay, you can observe in this formula, IA1 will be equal to E divided by Z1 plus Z2 plus ZF. Anyhow, they have not mentioned impedance, fault impedance, so this will be equal to 0. Then what is the formula? So only this one, that is E divided by Z1 plus Z2. You can observe from this formula that we need not calculate zero sequence impedance, right? There is no need of calculating zero sequence impedance for LL fault. This you have to remember. Only calculate positive sequence network and negative sequence network, and these two interconnection we can take. Okay, let's see how to solve this, right? So since as we have drawn the circuit diagram of this one, it is a generator. As we know, this is a generator, this is a transformer 3. Okay, based on that value you have to put. Okay, substitute all the values by taking. Okay, generator 1 is 0.3 and T3 is 0.1. Okay, so generator is 0.3 and T3 is 0.1. Please remember this, it is a T3 transformer. Okay, and similarly write all positive values, that is x1 values of each element, means each component. Generator x1, transformer 3 x1, line x1, line 2 x1, and all x1 values has to be substituted. And then how to deal with this? We need to calculate a total impedance first. Okay, equivalent impedance. So what we can do is, this is a delta form, right? Convert that into a star form. Okay, how we can do that? It is to be done, it is a delta, right? So take a point and then we can calculate like this, right? So this is how it looks. Calculate the calculations, all parts. Okay, so it comes like this, you know, this circuit diagram, delta connection. When you convert star, it comes like this. So this term, if you say it is a, b and c, then it will be a, b and c. Okay, this is a c form, right? So now you can observe a, b, l1 and all. If you convert, you get this one, 0.0357, 0.028j, 0.028j. Can calculate and place. Okay, check once you check the values of it and substitute all the values remaining as it is. Okay, and again convert this. Observe, fault is at here. Okay, so how these two resistances are in series? So 0.3 plus 0.1, it will be 0.4j, right? This is a 0.4j, and then fault is here, right? And the next, you keep this element as it is. And what about all these three are in series? So add 0.3j, 0.12j and 0.0228j. This comes 0.4485j. Okay, and then this is also almost all same only. Okay, so this is a 0.28, 0.028j, 0.12, 0.3. So same, all these are also of the same. Therefore your second means third branch will be of will have a same values. Okay, and then now what you can do is, so just observe, right? So now this is fault is here. Okay, so what we can do is, you can take these two impedances are in parallel to calculate that impedance. Okay, to calculate that impedance, what we can do is use the Thevenin's theorem. So make sure that key sources are short circuited. Okay, since we have a voltage sources, let them short circuited. So when you short it, so when you short these things, it comes like this, right? Substitute all the values. Alright, okay. So now these two are in parallel combination. Take that parallel combination, okay, and then keep as it is this value as well as this value. Okay, and once we calculate, these two are in series. Okay, and then you can add those two and place here. This is a fault point, so when you are stretching these two will be in parallel. So take that parallel combination impedance. Okay, therefore your positive sequence network will be of one impedance, totally means equivalent impedance with voltage source, that is considered as 1 at an angle 0 per unit. And next, let's see negative sequence network. Same, now we will draw one more time of this. Draw the one more time. Okay, observe, this is a delta connection. Please remember one thing, that don't consider same as that of positive. Okay, here this is a negative, and whatever the values they have given are of different values. You can observe x2 of this one is different, x1 is different, x2 is different, x1 is different and x2 is different in most of the cases. Okay, so according to that we have to write. Okay, so then don't directly, you don't write blindly. Okay, So all the values are equal, because earlier we used to do the same thing. Okay, here it is bit different, that values you have to substitute. Same thing you do, that is convert this. Okay, convert this delta into a star. Okay, so convert this into a star, and these two will be in series, and whatever you have converted, these things will be in series, and this you keep as it is because fault is at here, and these two are in series. Okay, do the same thing how we have done in earlier case. So when you solve this, you get a simplified one in this way. Okay, these are the values. And next, if you further simplify, that is these two are in parallel combination. If you do this parallel combination, and parallel combination along with this is in series, so directly we have taken calculate and check the value once again. Okay, now if you are considering between the fault, then these two will be in parallel, so take a parallel combination of that. It comes 0.124j. Okay, right, now we have got z1 or x1 equivalent and x2 equivalent. Let's connect it interconnected system. Okay, let's consider interconnected circuit diagram. Okay, just it is to find the fault current of LL. Okay, so as we know, this is a positive sequence and it is a negative sequence. Okay, network. So where is the fault? Where is the fault? Fault is at this condition. So whatever current flows, it will be flows in this direction, and whatever I2 comes, it is in that this direction. As we know, IA1 will be equal to minus of IA2. Minus of IA2. Okay, that we need to calculate. Let's calculate IA1. Okay, as we know, it will not consider any zero sequence value, so that's what we have not considered, and we have not calculated the zero sequence. Let's see IA1 how to calculate. IA1 formula we have is nothing but your minus IA2, since those two directions are opposite. So EA will be equal to Z1 plus Z2 plus ZF. Okay, ZF also they have not mentioned, so it will be 0. So just take a EA and substitute Z1 and Z2 values. Okay, so IA1 you get this much. Okay, therefore it will be equal to minus IA2. Okay, and then what about the fault current? Okay, fault current is, as we have said, IF into root 3 times of IA1. Okay, since it is a negative, we will take a magnitude of that. So then it will be root 3 times of the magnitude, 3.54 is nothing but 6.13 per unit. Okay, I hope you have got this. Thank you.